So welcome back. Do you remember what I taught you in my last class?
Yes, sir.
What was that?
Today's PD full form in full swing.
Okay. No, I promised you that I'll be dealing with some real PD, right? Okay. But I still don't know whether I'll be able to do that or not. Hopefully, we will do that. Okay. So if you recall, yesterday I did your integral curve of a vector field. Integral curve of a vector field. Okay. So if you recall, what was that? If I have a vector field say V, of course, it is a function of x, y, z, and if it is given by this functional relationship, right? So then if there is a curve C in such a way that at each point of the curve C, this vector V is a tangent, then we say that your what? That C is an integral curve of the vector field V. Is it okay? Fine. So I'll be doing some more concepts related to this integral curve, but before that, I'd like to take you back to something which I taught yesterday. Let me get back to this. Let me get back to these curves and their tangent. Curves and their tangent. Just one thing I would like to. Curves and their tangent. Okay. So yesterday, what I did, I told you about. Say, suppose I have one level surface given by U1 equal to C1, and similarly, if I have another level surface given by U2 equal to C2, I think I had taken F1. Anyway, it doesn't matter. F1 and F2. Okay. So then I told you that, or you rather agreed with me, or you guys told me that the intersection of these two surfaces, they are going to give me a curve, right? They are going to give me a curve, okay? And remember, this curve, I'm not going to get this curve all the time. And yesterday, I set one condition there. If this is not equal to 0, if it is not equal to 0, then what will happen? This is going to give me a tangent vector, right? Is it okay with everybody?
Yes, sir.
Right? See, why that is so, before that, what we'll have to see. Like, suppose I have, let's say, two surface, say this is say U1 equal to C1, and suppose I have got kind of another surface, suppose this is U2 equal to C2, okay? And then, if they have to intersect, so definitely, the set of their points of intersection, it has to be non-empty, right? That is the very first prerequisite, isn't it? Fine. So now, let us get back to this. Let us get back to these two. What does it tell you is that, as you know, that your grade U1, it is nothing but grade U1 at a particular point, say. Grade U1 at a particular point, say x0, y0, z0. Particular point, what is happening in that point? This is nothing but a normal to the surface at that particular point. Similarly, like say, I can have grade U2 at the same point, that is going to be a normal 2D surface U2 equal to C2 at that particular point, right? So now, what does this do? It prevents those normals to be parallel. Is it okay? Is it okay with everybody?
Yes, sir.
Right? Okay. So again, if they are parallel, then we may not get these two surfaces intersecting at the point x0, y0, z0. Because if they are parallel, like say one surface may look like this, one surface may look like this, another surface, say suppose this is my point x0, y0, z0. This is my point x0, y0, z0. Okay, so what will happen? What will happen? I may have something like, I may have a situation like this where they're both going to be parallel to each other, and then what is going to happen? In order to define a tangent, I am not going to get any direction at all, right? Or it may so happen that okay, you can define a direction along say grade U2, right? But the surface may be like, we may have some surface like this, we may have some surface like this. Where I am getting some normals at the same direction, right? That is the point. Like say, if they are parallel, we may not get a point of intersection there. Fine. So this is going to guarantee me a non-empty state as the set of points of intersection, and not only that, it is going to give me, as you have already pointed out, it is going to give me what? A tangent vector at each point. So now again, yesterday we did some exercises where eventually curve say that not integral curve, sorry. From the point of intersection of two surfaces, this, what we did eventually, if these two surfaces had intermediate curve C, I was able to get a parametric expression for this curve so that this curve can be expressed in terms of this vector xt, yt, jt. Right? Okay. Is it okay? We have already done that, right? For a particular example. You know that was possible. So now what I would like to tell you, I would like to tell you why this is possible. Why this is possible. Yesterday I didn't explain that to you. Why this is possible? It is very simple. See here, if I want to find out this one, so you know that this is nothing but your del u1 del x, del u1 del y, del u1 del j, and then del u2 del x, del u2 del y, del u2 del j, right? And you will see that this is nothing but simply your Is it okay with everybody? Yes?
Yes, sir.
Right? So now the assumption that this is not equal to the zero vector, it is going to guarantee me that at least one of those components at least is non-zero. Is it okay? Fine? Okay? So then, suppose I am assuming that the first component is non-zero. So then I am going to have something like this. I am going to have Say, suppose this is not equal to 0. See here, you should say, well, one is a vector and one is a scalar. Okay, fine. So now what happens? What happens? You know the implicit function theorem, right? So if you use implicit function theorem for three variables, as a consequence of that, I'll just show you. We can get a theorem. We can get a theorem. Just have a look at this. Yes. Just have a look at this. See, their ordering of x, y, z is different. This is just to emphasize on the x. This is just to emphasize on x. Okay. So basically, what it tells you, see, these are nothing but something like u1 equal to c1 and u2 equal to c2. Okay. So then what is going to happen? Like if this Jacobian is non-zero, it is of rank 2 bits, and this is non-zero. Okay. If the Jacobian is non-zero, then what happens? In the, non-zero, like say, at a particular point, say, right? So then what is going to happen in the neighborhood of that point? What is going to happen? You will be able to express y and z explicitly in terms of x. That is what it says. Is it okay with everybody? Is it okay with everybody? Let me assert you that this is nothing but a consequence of implicit function theorem. Okay, fine. So I think now I have been able to convince you that there is a consequence of implicit function theorem. So basically, from here, the consequence of implicit function theorem, it asserts us that I can express y as a function of x and z also as a function of x. Is it okay? Fine. Yes. So that means by simply parametrizing it through x equal to t, then your y equal to zt and z equal to ht, right? I can define the curve C. Through a vector, your rt given by your t, gt, ht, right? ht in space for some t line in some interval I. Is it okay? Fine. So this is what is going to guarantee me. A curve, right? As the intersection of those two, level surfaces, right? And I'll be able to find a parametric representation of that curve. Okay. So this part I require today. I'll prove one theorem. So I'll just simply tell you that okay, now because of this gradient of u1 cross u2 being not equal to 0, this is definitely going to guarantee me a curve of intersection. That's it. Okay. So that is why I have wrote this. So this is done. Now let me go back to your integral of a vector function. Integral curve of a vector function. Okay, fine. So now, say, suppose the vector field is given by say PQR. So basically, PQR, they are functions of x, y, and z. Okay, and I have defined them in some omega, reason omega, which is a subset in R3. Okay, so now what is happening here? If C is the integral curve corresponding to this vector field V. V. Suppose it is C is something like that. C is something like this. So then, if say this space curve, suppose this space curve, I mean it is defined through, say at each point, sorry, should I use P here? Because I have already used P. Okay, suppose I call it P tilde, huh? This point. So with every point P tilde lying on the curve, suppose it is defined through this vector. It is defined through this vector. Okay, and suppose it can be parametrized. So that this curve you can define through this, or some t belonging to some interval i's. Okay, so then what is going to happen? I mean a tangent vector to this curve at a point is given by simply this vector dx dt, dy dt, dz dt. Okay, so that is why, because say this is the tangent vector, say t bar, and I know that the vector field V is such that what happens? V is such that what? If C has to be the integral curve of V, then what happens? Are you guys here?
Yes, sir.
Yes, sir.
That yes. What is the relationship between V and that curve C? If C is the
V will be tangent to C.
Yes, V will be tangent to C at each point. Okay. So now, so that means there must be a relationship between the components of V and components of this tangent vector. Okay. See, I have already told you earlier, right? Whenever I define a tangent, I simply call it as a tangent vector, isn't it? You like say the vector, I mean, if its direction is the same, its length can be different, right? So, like say, so that means at a particular point to a curve, I can have infinite number of tangent vectors, isn't it? Are you getting my point or not?
Yes, sir.
Right? So, in fact, there's an exercise, I'm going to show it to you. There's an exercise in your book, I'm going to show it to you. In fact, like say, these two vectors, they're scalar multiples of each other. Okay, they're scalar multiples of each other. And again, like say, that scalar, I mean, that multiple, that scalar multiple, like say, the factor, say, basically what I want to tell you is that this is going to be something like this. Okay, and this lambda, depending upon the value of t. So this lambda is going to be a function of t. Are you getting my point? Yes?
Yes,
Isn't
sir.
it? Right? Because say suppose I have say this as a vector. Suppose say this is V and suppose this is T. Suppose this is T. Again at other point, my V could be something like this and T could be something like this. So that means depending upon the value of T, I mean this lambda will be decided. Okay, so that is why your this V is simply your mu T some function. Okay, mu T and mu T has to be non-zero. Okay, definitely it has to be non-zero because I don't want the tangent to be vanishing here. Okay, is it all right? Fine. So that is why, see, it may be a bit confusing because they idea, I'll tell you. In this book, I mean, they have simply straightforwardly said that. So there is a relationship between this v and the tangent, and that is given by your di dt equal to p, dy dt equal to q, and dz dt equal to r. But you should not, I mean, when you are going to visualize it, when you are going to visualize tangent and the vector v, you should not think that they are both going to be equal. So now I am making a comment. See, from C being an integral curve of the vector field v, I can always get a relation like this. In fact, there is some, I mean, multiple hidden there. Okay, although they straightforwardly start with that, but all the, I mean, geometric comments, all the geometric conclusions that I am going to make, they are still going to be valid. Okay, because it is going to be in terms of tangent and normal only. Okay, and like say some scalar multiple being present there, it is not going to make any difference to the geometry of all these things that we are going to discuss. Is it okay? So basically, what they say is that your with the vector field v given by the components p, q, r, we associate. They simply say that we associate this system of ordinary differential equations. So we are simply associating it. Okay, but the actual relationship is going to be given by this. Always remember. Okay, fine. And why they say this? Because I mean, you should be able to geometrically relate to this. So whenever you have something like this, you should remember that at a particular point, if you draw a tangent, then that components of the tangent, it is going to be proportional to p, q, and r. So that is the way we are going to relate it. Is it okay with everybody? Fine. See, I'm simply telling you to geometrically visualize this stuff from this relation. Okay, fine. Now, just let me show you the exercise. After that. Yeah, can you see it? Can you see it? This one. This is exactly what I told you just now. Let's see an integral curve of vector field v given by PQR, and suppose that C is given parametrically by the equations this: x equal to xt, y equal to yt, and z equal to zt. Of course, t belonging to some interval I, where the functions you already know that, I mean, they have to be, I mean, first order partial derivatives must be continuous there. Okay, and the tangent vector, this we assume that this never vanishes for that interval. So then you have to show that there is a function mu of t, again, like say it's first order derivative exists, such that for every t belonging to I and mu t not equal to 0, this happens. This we have already proved. And the second part is straightforward. It is simply chain rule. I am giving it as a homework for you. Okay, I am giving it as a homework for you. Okay, fine. So now let me just So again, if this happens, then you know that. Say suppose your p is say not equal to 0. Suppose p is not equal to 0. So then definitely what is going to happen? Your dy dx, this is going to be q by p, and dz dx, this is going to be r by p. This is going to be R by P. Is it okay with everybody? From these relations. From these relations, if P is not equal to 0, I can always get that. Is it okay?
Yes,
Right?
sir.
Right? So similarly, if Q is not equal to 0 and R is not equal to 0, you can have, two more relationships like this, and you know what those relationships are going to be. Is it okay? Fine. So what those relations are going to be, not relationship. So then, obviously, from these two ratios, what I'm going to get, I eventually get right. I can get this. Again, say here by assuming P not equal to 0, P not equal to 0, I have got this. But that doesn't necessarily mean that your R cannot be 0 or Q cannot be 0. Isn't it? See, I want simply at least one of them to be non-zero, right? So that the integral curve in connection with a vector field can be defined, or the integral curve exists. Is it okay? So you shouldn't even bother if some of them are equal to 0, but at least one of them has to be non-zero. Okay. So if this is 0, so in order to solve this, definitely you can adjust accordingly, isn't it? Basically that is going to give you Z equal to constant. Is it okay? Fine. Isn't it? Because say, if you look at this, say suppose R equal to 0, from here itself, you know that Z equal to constant. Is it okay? Fine?
Yes, sir.
Fine? You guys have become less and less vocal. Huh? So, okay. Now, okay. Let me come to the concept of functionally independent functions. Of course, we are considering functions of 3 variables. Okay. Before giving you the definition, let me again get back to, say suppose I have a function u1 xyz, okay, and I have another function, say u2 xyz, u2 xyz, okay, and suppose I am defining them in some omega in R3, some region omega in R3, right? So now, can you tell me what could be the consequence of this? What could be a consequence of this? Consequence of this statement? Yes? What could be a consequence of this statement? Yes?
Those two vectors are linearly independent.
Okay, apart from that, whatever you have learned yesterday from there, I am trying to rope in a curve. I'm giving you a clue. I'm trying to rope in a curve here.
We will get a parametric representation of the curve.
Okay. Say yes. So parametric representation we will be able to get. But before that, see here, I didn't equate u1 and u2 to something. I didn't equate u1 and u2 to something. But definitely by equating them to constants, you can get some level surfaces, right? Okay. And then, irrespective of whatever be the value of this constant here, this is equal to C1 or C2, what is going to happen? What is going to happen if the cross product of their gradient is non-zero? It is always going to guarantee me. It is always going to guarantee me what? A curve of intersection which can be parametrized. Is it okay? Is it okay with everybody?
Yes,
Fine? Right? So that is what. So basically these two functions u1 and u2 defined in a region omega in R3, they are called functionally independent. Functionally independent if this happens. That's it. That is the definition of it. That is the definition of functionally independent. Okay.
Sir, what
Yes.
is the guarantee that it will be parametrizable? Please repeat again. What is the guarantee?
No, I have already told you. I have already told you. Like if this is non-zero, if this is non-zero, so that means at least one component of this cross product. Like this is going to this one. It is going to give you a vector, isn't it? It is going to give you a vector, right? Something like component say f1, f2, f3, right? So we have already seen that. Like say one of them, if at least one of them, then what we can from the implicit function theorem, what we can do, one of the just a minute. Let me again. Then and that concept we derive from assuming that we already have two level surfaces, right? What it is going to guarantee you that, like from I have already told you, I have shown you in the slides also, right? So then what was happening? Y equal to some g of x and z equal to some h of x, isn't it? I always
Yes,
got
sir,
something
yes,
like this,
understood.
isn't it? Then by setting x equal to t, you can easily get a parametric representation of the curve of intersection. Is it okay?
Yes, sir.
Right? Right? Okay, fine. So now let me try to find out the relationship of this definition with a vector field or with an integral curve of a vector field. Whether we can do or not. Well, this is done only to establish some relationship between all these. Just a minute. Okay. Okay, suppose C is the curve of intersection of these two surfaces. C is the curve of intersection of these two surfaces. Okay. Suppose, as I did yesterday, suppose I have something like this. Say, suppose this is equal to U equal to C1, U1 equal to C1. This is U2 equal to C2. And suppose this is their curve of intersection C. This is their curve of intersection C. So now, okay, obviously what you have seen, that I have something like this. This is grade of U1, and I have something like this. This is grade of U2, grade of U2. Okay, let me not do anything else with the cross product of these gradient vectors. Okay, fine. Now, suppose this C, See, forget about the presence of the surfaces u1 equal to c1 and u2 equal to c2 for the time being. Just think C as an independent curve lying in space. Is it okay? Fine. Now, what is going to happen? What is going to happen if C is the integral curve of the vector field V, then what must happen? What must happen? At each point of C, V must be a tangent vector. Fine? Is it clear?
Yes, sir.
Right? I mean, I'm just simply thinking C to be independent of u1 and u2 for the time being. Okay? So then from the definition of integral curves, I mean corresponding to a vector field V, definitely V has to be tangent at each point of the curve C, right? So that means if I consider this point x0, y0, z0, now let me bring the surface to C1 and u2 equal to C2 also, right? So then at that point, to the curve C, your V must be a tangent, right? V must be a tangent. Clear?
Yes, sir.
I don't see the confidence. Okay, fine. Okay, fine. Okay, suppose I am considering a curve. C in space. Okay, so then if this curve C is an integral curve for this vector V, so then what must happen at each point? V must be a tangent to the curve. Okay, so suppose I'm simply thinking about a fixed point, say x0, y0, z0. Okay, now suppose this C is nothing but the curve of intersection of the surfaces, curve of intersection of these surfaces, your u1 equal to c1 and u2 equal to c2, right? So then what must happen? If I draw a normal which is given by grade u1 at this point, and if I draw another normal grade u2 at this point, now you are getting my point, right? So now what I am doing, I am taking this curve C, which is an integral curve for the vector V, as the curve of intersection of these two surfaces. Now it is clear. So now what I have done, after that, I have considered these normal vectors grade u1 and grade u2 at the point x0, y0, z0 corresponding to those two surfaces. Up to this clear now? I want at least 2 yeses.
Yes, sir.
And what happened to the girls? I haven't heard from them for a while. Yes? Nobody is wanting to answer. Anyway, okay. So now.
Yes, sir, it is clear.
Yeah, but they are silent. I mean, say I should have the guarantee that everybody has understood it. Okay. Say now, yesterday itself I explained to you that what happens, your grade U1, if this V is the tangent, so then what must happen? These two must be perpendicular, right? V and grade U1 must be perpendicular to each other. This is straightforward, right?
Yes, sir.
Isn't it? So similarly, grade U2 Fine? Isn't it? Fine? So this is going to give me, now if the vector V is given by PQR, so this is simply going to be your P del U1 del X plus Q del U1 del Y plus R del U1 del Z equal to 0. Similarly, from the other one also, I will get this. See, probably you have solved, I mean, all these differential equations, I mean, before, all these differential equations before. But I now, being PhD students, I want you to relate them to some geometry. So, up to this, the concept is fine? Yes? Right? So,
Yes.
that brings me to the concept of first integral. That brings me, see, these two, it brings me to the concept of first integral. So what is the concept of first integral? So as before, what we are going to do, we are going to consider a function ux, yz in some reason omega in R3, right? So then this ux, yj, this is going to be called a first integral of a vector field V given by say PQR, if, so basically this one, gradient of V equal to 0. Okay, so that means your P del U del X plus Q del U del Y plus R del U del Z equal to 0. So first integral. So uxyj is going to be called the first integral of the vector field given by this if grad u dot v is equal to 0. So that means p del u del x plus q del u del y plus r del u del z equal to 0, and of course that happens in the prism omega. So far so good, right? Yes?
Yes, sir.
Yes.
Right? Okay, thanks. First integral, it is done. Okay, so now I will come to two theorems. You will see that they are very, very interesting ones. Let U1 and U2 be two functional independent first integrals of a vector field V, of course it is going to be defined in some omega, okay? In some omega, say in R3. So then the surfaces I don't know whether they are still calling them surfaces, but geometrically they are nothing but surfaces. Then these they simply say the equations. Let me stick to them. we also call them equations, but they are nothing but surfaces. Then the equations, these two describe the collection of all integral curves. This describe the collection of all integral curves of V in omega. That's it. So this is the theorem. This is the theorem. I think you are already getting some clues about how to go about it. See, I'm going to give you an outline of this proof. Okay, outline is, of course, I'm going to prove it, but the writing part may be absent. And you please go through Simon's book again. Okay, fine. So, how to prove this? Okay. Proof. See here, we have like what we have. We are given two surfaces. U1 equal to C1 and U2 equal to C2, right? And what additional information we have, the very crucial information that we have is that both U1 and U2, they are first integrals. They are first integrals, right? They are first integrals of the vector field V. Is it okay? They are first integrals of the vector field V. So what does that mean? Okay. So firstly, what I am going to do, I am going to consider what? The curve of intersection of the surfaces given by these two. Is it okay? Fine. Let's say, should I write it as C or? Okay, fine. Let C be the curve of intersection of, say, this one of one. Okay, fine. So then, can I say that C is an integral curve of V? Yes. Yes or no? Yes or no?
Yes, sir, I think.
Not you think. You have to tell me why you think so. Okay, let me tell you. It is very easy. Okay, fine. See, this curve, suppose this is the curve C. Okay, so what happens? This curve, lies on this surface, say U1, as well as it also lies on, say, another surface, say U2. So this is U1 equal to C1, U2 equal to C2, right? What else do we have? You know that U1 and U2, they are first integrals of V. So that means V and grad U2 dot V, both of them are going to give you 0, right? So that means, and again, see, if you consider all the points lying on this curve C, right? So then what is going to happen? Like if you draw a tangent line at each point of those of the curve, then what is going to happen? This normal, right? This normal is going to be what? Perpendicular to V, isn't it? This normal is going to be perpendicular to V, right? So obviously, then what is going to happen? V must be tangent at each point to the curve from these two relations. Isn't it? Are you getting my point?
Yes, sir.
Yes, sir.
Right? Right? So that is why this curve C, which is nothing but the curve of intersection of these two surfaces, it is an integral curve of V. That is the first part. Okay, that is the first part. So the theorem is about that these two equations U1 equal to C1 and U2 equal to C2, it is written that they describe the collection of all integral curves of V in that region. Okay, so now next time what we have to do is that we are going to choose an arbitrary curve C. We are going to choose an arbitrary curve C, which is an integral curve of V. We are going to choose an arbitrary integral curve C of V. Okay, so then we are going to prove that it is nothing but what? It is nothing but the intersection
Curve of intersection.
Yes, those two surfaces U1 equal to C1 and U2 equal to C2. Okay, fine. Now one thing. Okay, fine. So how to go about this? See, suppose this is an integral curve of V. This is an arbitrary integral curve of V. Okay, and suppose I have considered a point x0, y0, z0. I have considered a point x0, y0, z0 here. Okay, so now let us choose, because this C1, C2, I mean, maybe misleading to you. Okay, so now let's say U1 x0, y0, z0 equal to say a constant. So similarly, say U2 x0, y0, z0. Say suppose this is equal to v. Is it okay? Fine. For the time being, it is fine, right? So then, what is going to happen? Now, if I choose the surfaces, say U1 xyz equal to a, right, and U2 xyz equal to b, right? So then definitely the point x0, y0, z0 is going to lie what? Going to lie in the curve of intersection of these two surfaces. Agree or disagree?
Agree, sir.
Agree, right? Oh, isn't it? See, I am not roping in C1 and C2 because you'll be thinking that firstly, I have seen the surface, then I'm trying to make some comment here. Okay, so see here why I am using A and B. You can definitely use C1 and C2. C1 has used C1 and C2. But that may be a bit confusing. Okay, see what I have done. I have chosen two constants. Okay, I have chosen those two constants in such a way that they are nothing but the value of the functions u1 and u2 at the point x0, y0, z0. Okay, fine. So then I have created two level surfaces by equating those functions u1 and u2 to a and b respectively. Fine. Up to that, it is fine, right? Okay. So then what is going to happen? Then what is going to happen? And if you say C prime, if C prime be the curve of intersection of the surfaces, this U1 equal to A and U2 equal to B. So then we have already seen that C prime must be an integral curve of V. Isn't it? C prime must be an integral curve of V. Is it okay?
Yes, sir.
Isn't it? We have at the very beginning, we have already seen, right? So then what is going to happen? So now can you prove that, I mean, C is nothing but C prime? Yes? Can you? Yes, can you now? I have got two integral curves. I have got two integral curves, C prime and C. Both passes to the same point, x naught, y naught, j naught. Okay, right? So can you give me a way of proving that C prime is nothing but C? How is it going to come? Both are integral curves of V. Then what happens? There is an associated system of equations, right, for V. Are you getting my point? We have already told earlier, and that is nothing but dx dt equal to P, dy dt equal to Q, and dz dt equal to R. Is it okay with everybody? Fine. So now we have a system of equations. System of equations in 3D, right? System of equations in 3D, right? And we have an initial condition. We have an initial condition, which is the same for both these curves C and C prime. Are you getting my point? Right? So from existence and uniqueness theorem, though that particular system, it must give me a unique solution, right? And that is why they must give me the same solution curves, isn't it? So C1 and C prime, they must be the same curve. Okay, so I'd like you to again go through this at home again. Like you please go through CMOS. I mean, he hasn't explained more than me. That I can guarantee. He has explained much less than me. Okay, fine. Okay, so then there is another. I mean, this is just a mechanical theorem. I don't know whether you have been able to appreciate what we are going to do later on. Maybe, I mean, you guys are so silent today. Maybe. Okay, let me tell you something in advance so that your energy is back. See, earlier, you know, in your BSc and MSc, probably you must have solved equations like this many a times, right? Dx by P equal to dy by Q equal to, right? And if you recall, like say these solutions were like what? What did you get from there?
Two surfaces.
Exactly. You got something like Agree, everybody agrees, right? Isn't it?
Yes, sir.
Yes, sir.
And
Yes,
again,
sir.
thank you. And again, the solution procedure was very simple, right? You found it very easy, like, oh my God, this is so good. Lagrange's multiplier, cheaply apply. And then, 10 out of 10 in exam is guaranteed, right? So now, are you getting a hint of relating the solutions to something geometrically? Are you getting a hint now? Some hint?
Yes, sir.
Now? Yes?
Yes.
Okay. Try to develop on that hint. You are going to get everything. You are going to get everything. See, earlier we did everything mechanically. That is what I told you at the very beginning of this course. That it is not only about earning mark, it is about, learning the concepts, geometrically. Okay, so that is going to make your mathematics more beautiful. And because, see, most of you are going to be teachers later on. So in that way, you will be also able to teach your future students, in a much better way. Okay, fine. So something is coming. Something is coming because I thought that today's class was a bit dull because I didn't get that much response from you guys. So that is why I thought that if I give you this idea, okay, it should excite you. And if it doesn't excite you, then I'm a failure. Okay. So then I'm doing another theorem. Okay. So I just tell you that this is pretty straightforward. See what it is. Fu. So this is a C1, single variable function. Single variable function in U. And again, your U xyz, and this is a first integral of the vector field V. First integral of the vector field V. So then obviously I can define a new function. So this is simply your f of uxyz, right? F of uxyz. Okay. So this is also your first integral. First integral of V. Okay. And this is say theorem A, and B part is likewise. B part is likewise. And again, this is again a C1 function in two variables U and V. Two variables U and V, and your uxyj and vxyj both are first integrals of V. Then you have to show that. The function f of u comma v is also a first integral. Maybe now this function, the new function, say something like w. So this is equal to f of this uxyz comma vxyz. So this is also a first integral of. This is also a first integral of what? V. Okay. So what I'll do, I'll just give you a hint of only the second one, and the first one will easily come out. Any idea how to go about it? Okay, fine. Let me do the proof of this second. Let me do the proof of this second. I'll just leave the proof halfway through. So you'll see this pretty straightforward. Okay, fine. So I have been giving that u and v, they are your first integral of v, right? So that means your grade u dot v and grade v dot v, this is equal to 0. This is equal to 0. Is it okay? Fine. So now I have to prove that grade w, this is equal to 0. I have to prove this. Is it okay with everybody?
Yes, sir.
Right? So then now this is equal to what? This is equal to what? R, right? This is equal to this. Because if I assume V to be equal to PQR, right? And W is a function of U and V themselves are functions of X, Y, and Z, right? So then what is going to happen? So this means this is going to be what? Del W, del U, del X plus del W, del Y. Del W, del V, del X, isn't it? This into P. Is it okay with everybody?
Yes, sir.
Right? So similarly for this also I will get, this also I will get 1, and this also I will get 1. You know what to write. So then you will see that del W, del U, and del W, del V, it will be present there in all these three brackets. So that means if you take out del W, del U, so I am going to get del U, del X, P plus del U, del Y, Q plus del U, del Z, R. Okay, so similarly from here, del W, del V, again this is going to give me what? Del V, del X, P, and so on. Right? And from this relation, this part is 0. From this relation, this part is 0. Is it okay? Fine? Is it okay with everybody?
Yes, sir.
Right? And then the proof is complete. Okay? So that means, if I have a first integral corresponding to a vector field, right? From there, I can create infinite number of first integrals. Is it okay? Is it okay?
Yes, sir.
Right? And let me again tell you another thing. Just a minute. I got to do some exercise. Just a minute.
Sir,
Yes. Yeah,
sir,
please
I
go
have
on.
one question.
Yes.
I just want to ask that here you choose only one parameter. So,
Yes.
but in higher dimensional, in differential geometry, there we can use more than one parameter. But for that, for those cases, how we deal these problems for higher dimensional?
Oh, you will see. I'll do later. I'm going to use S and T later on. Don't worry about it. It will unfold. Okay, it will unfold. It is, see, depending upon the problem, I'm going to use more than one parameter also. Don't worry about it. In fact, I'm going to use definitely. I'll use later on. Don't worry about it. Now I just and again say, as I have told you, the parametrization is not unique. Parametrization also in terms of a single parameter is also not unique. You should remember that. So there's an exercise that I have did. I had say this exercise, like say, I think V is equal to mu T into the tangent vector, mu T into the tangent vector. So after this, there is an exercise. That exercise tells you that you can use, I mean, more than one. I mean, you can have more than one parametric representation. Okay, so you please prove that. You please prove that. I'll do that two parameterization later on. One
Yes,
I
sir.
want to take.
Different
Yes.
parameterization is we can do different parameterization, but here I am taking the parametric.
No, I understand. You are talking
variability.
about, see, you are talking about not single parameter, right?
Yes,
You
I
are,
am taking T1, T2. They are linearly
I
independent
understand.
parameters,
Yes.
and more
yes.
than that.
I understand that. Yes. You are talking about using more than one parameter.
Yes.
And again, I'll just do one exercise, and from there I am going to make a comment. Example 1.2. Just I was looking something for 1.3, just a minute. I was looking for a harder exercise, but again, firstly, you have to show that your yz by x squared and y squared minus z squared by x squared, they are functionally independent. Functionally independent. That is one thing. Independent first integrals of, I think V. Here they are using some other V in this. I think there's a printing mistake here. That is why I got a bit confused. Okay, and then you have to verify that. Yz by x squared equal to c1 and y squared z squared. Again, the same thing. X squared equal to c2. It describes the same two-parameter family of curves in omega, but that omega still hasn't been given to you. That is okay. Fine. I got it. Just okay. Fine. Okay. Fine. Sorry. Okay. See here. Firstly, what we have to prove that these two functions. So I told you that u1 and u2, they are functions of x, y, z. Okay. So firstly, you have to prove that they are functionally independent. So basically, what you have to prove, grade u1, grade u2 is not equal to 0 bar, not equal to 0 bar, and here omega is this is your R3 minus that origin. Omega is R3 minus origin. Okay, fine. So this is the first part, and then you have to prove that both of them are first integrals of V. That you can easily prove. What you have to do, you have to simply do this dot V. This is equal to 0. Similarly, this is also equal to 0. What I'm more interested, that these two describe the same two-parameter family of curves. Same two-parameter family of curves. Are you getting my point? Are you getting my point?
Yes, sir.
Yes, sir.
So basically, what it is telling you is that when you get that curve of intersection, as an integral curve of some vector field, So the curve of intersection coming out from two surfaces, they are not necessarily unique. From different surfaces, it can generate the same curve. That is what my point is. Okay, please do this exercise. I have taken it from I have taken it from CMOS. I think in your slides also, I am going to upload it. So in your slides also, it is going to be there. Okay. So with that note, I think I'm going to finish my class today. Also, I couldn't reach to actually solving a PDE, but again, I mean, you have enough. For today. I have to go a little bit slow here because this geometrical concepts. I mean, sometimes one gets confused with them. Okay, and please go through whatever I have taught today once again. I mean, if you want to make your geometric concept solid, you have to go through it once again, and in one go you may not get it. Okay, so hopefully, and not hopefully, definitely tomorrow I'm going to start with solution of PD, and I'm going to start with very easy one, that is like dx by p, dy by q, and dz by r. I'm going to start with this. Okay, and probably I'm not going to emphasize much on the solution technique because you have already learned that. I'm going to emphasize more on the geometry part. Okay, so with that note, I am